Hi class, welcome back to thermodynamics. In this lecture, we're going to be looking more closely at the Carnot cycle, specifically the power cycle and the refrigeration and heat pump cycles. And so then we're going to go through some exercises together. So let's get started. So this is the Carnot cycle, and the Carnot cycle consists of 4 internally reversible processes. And let's look at the PV diagram at the top left here. And so this example is for gas in a piston cylinder assembly, and this would be a power cycle. So starting with state 1 in the bottom left here. So at state 1, you can see that the pressure is fairly low, the volume is relatively low, and these golden dashes represent isotherms, so lines of constant pressure. And so along this isotherm here at state 1, we're going to be at our cooler temperature, so T sub C. Okay, and so for our first process, 1 to 2, we're going to be riding along an adiabat. And an adiabat is where we don't have any heat exchange. And so we're not getting any heat exchange, but we're increasing pressure. So this is compression, adiabatic compression. So we're reducing volume slightly, we're increasing pressure, and what happens when you increase pressure is that you're going to also increase temperature. So this is going to bring us up to TH, to our higher temperature here. So we have adiabatic compression to TH, and so then from 2 to 3, so process 2 to 3, we're riding along an isotherm. So we're going to remain at TH, and in order to make that happen, under expansion here, so under expansion, we're going to be decreasing our pressure. And so in order to maintain the same temperature, we have to have a heat input. So for process 2 to 3, we have isothermal expansion with energy coming from our hot reservoir. And so then for process 3 to 4, once again, we are riding along an adiabat. And so we have adiabatic expansion to our cooler temperature. So we have a reduction in pressure and we have an increase in specific volume. And then lastly, process 4 to 1 brings us back where we started because this is a reversible cycle. Remember, Carnot is a theoretical cycle. It places the upper limit on engine efficiency. And so from 4 to 1, we are along an isotherm again. We are at TC and we have compression with the energy going to QC, our cooler reservoir. So that way we maintain this cooler temperature even though we are increasing pressure. Okay, so that is the Carnot power cycle. So you can see there it alternates between adiabatic process, isothermal, adiabatic, isothermal. So these are our 4 internally reversible processes. Okay, next, at the bottom left here, let's look at an example of a refrigeration or a heat pump cycle. So with this, we're going to start once again at the bottom left of our PV diagram at state 1. And once again, down here along this lower isotherm is our cooler temperature, and along the upper isotherm is our higher temperature. Okay, so process 1 to 2 is isothermal, and we are going to expand at our cooler temperature with energy coming from our cooler reservoir. So remember, with a heat pump and refrigeration cycle, we're inputting work to force heat to flow from the cooler reservoir to the warmer reservoir. And so then from process 2 to 3, we have adiabatic compression all the way up to our higher temperature. So we're riding along an adiabat here. We have no heat exchange, and so all the way up to our higher temperature. And so then from 3 to 4, we're riding along an isotherm, and we have isothermal compression, so an increase in pressure with energy going to the warmer reservoir, so QH, to remain at TH. Okay, finally, process 4 to 1 brings us, we follow adiabatic expansion, so we get a drop in pressure all the way down to our cooler temperature. So with the refrigeration and heat pump cycles, for Carnot, we start from isothermal expansion, we then have adiabatic compression, isothermal compression, then adiabatic expansion. And so when we go through problems following the idealized theoretical Carnot cycle, we are going to apply this template for these processes, okay? So whenever you're plotting it, and for the processes, use this as a template. It's an excellent starting point. And the one final thing I want to draw your attention to is, let's look at this area inside the curve here, and the area inside the curve here. Well, so what happens if we integrate PDV, for example? Well, we get work. And so for this one, work out is our area under the curve, okay? Or our area within the cycle. And so for the refrigeration and heat pump cycles, WN is the area. So just keep that in mind. All right, so I'm sure you are excited to go through some exercises together now. Now, this is number 77 from chapter 5 in our book, and we're going to be referring to the Carnot heat pump cycle. So if our initial pressure is 14.7 and P4, so pressure at state 4, is 18.7, each in pounds per square inches. So yes, for this one, we will be using the imperial system. And our specific volume at state 1 is going to be 12.6, and our specific volume at state 4 is going to be 10.6, and each are going to be in cubic feet per pound. Okay, and the gas is air, and it obeys the ideal gas model. So we are tasked with determining TH and TC, each in degrees Rankine. Remember, we have to use the absolute, we're using the absolute temperature scale here, and we also have to find the coefficient of performance. So let's just start by rewriting down and summarizing what is given. So given, we know P1 is 14.7 pounds per square inches. We know that P4 is going to be equal to 18.7 pounds per square inches. So V1 is going to be 12.6 cubic feet per pound. And V4 is 10.6 feet cubed per pound. So remember that down here, states 1 and 2 are at TC, and states 3 and 4 are going to be at TH. All right. So the thing is, we're given information for state 1, so that we could potentially find TC given that information. And we're given information about state 4, so we can possibly figure out T4. So we are tasked with finding TH, TC, and the coefficient of performance for a heat pump cycle is going to be gamma. And then just also with the given, let's just write down that we're dealing with air. Okay, and it can be modeled as an ideal gas. Okay, so let's go forward with the solution. Okay, so a good starting point, considering we're modeling air as an ideal gas, would be the ideal gas law. And so that's going to be PV is equal to R air times T. And we're going to ultimately have to solve for T, because we're looking for TH and TC. So T is going to be equal to PV over R air. And just remember that, so dealing with English units, R air is going to be 0.06855 British thermal units per pound degrees Rankine. Okay, so let's start with T1, which will be our cooler temperature. So T1 is going to be equal to P1 V1 over R air. So we have 14.7 pound force per square inch times, all right, so in this case, because we are given volume in cubic feet, we're going to want to convert square inches to square feet, and so our conversion factor there is going to be 144, right, 12 squared, because there's 12 inches per foot, inches squared per foot squared times 12.6 feet cubed per pound. And we're going to divide by 0.06855 BTUs per pound degree R. And we're going to have to do another conversion here, and that is that there's 778.17 feet times pound forces per BTUs. Okay. And so let's just go through and check our units. So we'll do a little dimensional analysis here. And so we have a pound force up here, and we're dividing by a pound force down here. let's see, we have our inch squared. Let's see, we have a foot squared here that we're divided by. We have a foot cubed here that we're multiplying by, so we're left with a foot, and then we're dividing by a foot, so all the feet cancel out. And then we're dividing by a pound in the numerator, and we're dividing by a pound in the denominator, so those cancel. We have a BTU in the denominator, and we're dividing by a BTU. And so we are left with 1 over 1 over degrees R, which is degrees R. Woo! Okay, so that works out, and this is going to be a very lovely number. It's going to be 500 degrees R. Okay, so that is going to be our TC. Okay, I'm going to open up a new page, and we're going to keep going. So this is still book 5.77. Okay, so far we know TC is 500 degrees R. Okay, now we have to get TH. And TH is going to be equal to T4. So TH is going to be equal to T4, and that's going to be equal to P4 V4 over our air. Okay, so once again, we have 18.7 pound force per square inch. Our conversion factor, 144 square inches per square feet times 10.6, which was given, feet cubed per pound. Then we're dividing by our air, which is going to be 0.06855 BTUs per pound degree Rankine. And our conversion factor, which is going to be 778.17 feet times pound forces per BTU. So here we end up with TH is equal to 535 degrees Rankine. All right, now we have our final step, and that is to determine the efficiency of our heat pump cycle. And so remember that for this, we're dealing with a Carnot cycle. So this is a theoretical efficiency. And so we're able, we're able to use the ratio of the higher temperature and the lower temperature, which is going to be the same as the ratio of the heat transfer for the hotter reservoir and heat transfer to the cooler reservoir. So gamma is going to equal TH divided by TH minus TC. And remember, these have to be in absolute temperatures, and we're dealing with Rankine, so we're fine here. So it's going to be 535 degrees R divided by 535 minus 500, so 35 degrees R. And this gives us an efficiency of 15.3. All right, and so we have two more practice problems to get through together today, so let's keep going. All right, so now we're going to switch back to metric units. Woo! And this is number 5.80 from your book. Air within a piston cylinder assembly executes a Carnot heat pump cycle. For the cycle, our higher temperature, T sub H, is 600 Kelvin, and our lower temperature, T sub C, is 300 Kelvin. The energy rejected by heat transfer at 600 Kelvin has a magnitude of 250 kilojoules per kilograms of air. The pressure at the start of the isothermal expansion is 325 kilopascals. Assuming the ideal gas model for air, determine A, the magnitude of the net work input in kilojoules per kilogram, and B, the pressure at the end of isothermal expansion in kilopascals. Okay, so once again, we're dealing with a heat pump cycle, and we're dealing with air and its ideal. So once again, 4 and 3, we are at TH. And 1 and 2, we're at TC. So let's go through our givens. So we're given TH. We're given TC. And then we are given the magnitude of the energy rejected by heat transfer at 600 Kelvin. Rejected by heat transfer at 600 Kelvin. Okay, so we're given the magnitude of QH. And I'm doing a little q because we're given this on a mass basis. So it's going to be 250 kilojoules per kilogram. And so the magnitude here is just telling us, it's not giving us a positive or negative sign. Okay, so it's just giving us a magnitude, not giving us the direction. The pressure at the start of isothermal expansion. So we have to look like, where is the start of isothermal expansion in this case? All right, so isothermal expansion is going to be from 1 to 2. And so we're given P sub 1 is going to be 325. And let's see what else. Assuming the ideal gas model. So first, for this part, we're going to find, and we'll do part B on another sheet. So we're looking for the magnitude of the net work in. And so part B, we're looking for the pressure at the end of the isothermal expansion. All right, and so B, we're going to be looking for P2. Okay, so let's get started with our solution. All right. Okay, so we're looking really for our W cycle here. Okay, so our W in. And we know, because this is a Carnot heat pump cycle, that our gamma is going to be equal to TH over TH minus TC, which is also equal to QH over W cycle. Or in this case, it's our WN. Okay, so we have our magnitude of QH, we have our gamma, we have our TH, we have our TC. We should be able to solve for our work going in, or our W cycle. So W in is going to equal QH over gamma, which is equal to QH times TH minus TC over TH. Okay, so the magnitude of Wn, so remember we're given the magnitude here, looking for the magnitude, mag, just to be consistent. So the magnitude of our work in is going to be equal to 250 kilojoules per kilogram, so that's our QH, times TH minus TC, so that's going to be 600 minus 300 Kelvin, and then we're going to divide by TH, which is 600 Kelvin. Okay, so the kelvins are going to cancel and we're going to end up with kilojoules per kilogram, which is what we're looking for. And we get 125 kilojoules per kilogram. Okay, so now let's try part B. So B, we're looking for P2. And so for this, we know that, so we're looking for P2. And we know that process 2 to 3 and 4 to 1. So 2 to 3 and 4 to 1 are adiabatic. So let's start with an energy balance. Okay, so with our energy balance, let's do this for process 1 to 2. Okay, because we are given P1, and I'll just write it over here to remind us. So P1 is 325. Okay. Oh, kilopascals. What am I writing? And you guys can't yell at me because this is just a recording. Kilopascals. Okay. So, looking at our energy balance, we're going to have Q12 minus W12 is going to be equal to U2 minus U1. And the thing here is that we can neglect kinetic and potential energy, of course. And so in this case, though, process 2 to 1, we're riding along an isotherm. And so is there going to be a difference between our specific internal energies if U2 if T2 is equal to T1? Say no. No. Okay. So that's 0. And so this is going to tell us that Q12 is equal to W12. Okay, right, because this is delta T is 0. Okay, and so let's start to think about some things. So W cycle in this case is going to equal QH minus QC. And so we know QH, we know W cycle from part A, and so QC, which is going to be our Q12, is going to be equal QH minus W cycle. Or WN, right? So Another thing we know here, okay, because this is an isothermal process. So here, isothermal, so we know that N is going to be equal to 1 for a polytropic process. All right, so with that in mind, then, we'll keep going. And we know that Q12 is equal to W12, which is going to be equal to R air times TC times the natural log of V2 over V1. Okay. And remember that R air is equal to 0.287 kilojoules per kilogram Kelvin. Okay. And the other thing, though, is that R air times TC is also going to be PV. Okay, so we're starting to put some pieces together, right? Because we're looking for P2. All right, and so we are starting to find, hopefully you're starting to see this path that we can follow to solve for P2. Okay, so we know that P1, V1 is going to equal P2, V2 for n equals to 1. And because that means pressure times volume is a constant. So now let us go through and solve for P2. So a couple things we can write. We know that the ratio V2 over V1 is equal to P1 over P2. So W12 is going to equal R air times TC times the natural log, and let's sub in for V2 over V1, P1 over P2. Okay, so that's going to be the same thing. You can do that. It's the same ratio. And this is also going to be equal to QC. Aha. So, QC over R air times TC is going to be equal to the natural log of P1 over P2. Okay, and so let's get rid of our natural log by, oops, sorry, I just disappeared for a second. I dropped all of my notes. Let me refind them. All right, I'm going to pause while I reshuffle. All right, back together. So, in this case, we need to solve for P2, and so let's raise each side. Let's do E and raise it to the power of QC over R air T. And so let's do EXP, the exponential of QC over R air T times. So this is just another way of writing a function. So this means e to the power of QC over R air times TC. That's just another way of writing it so we can put the exponent, make the exponent piece easier to read. And that's equal to P1 over P2. Okay, let's keep going. I'm going to open up one more fresh sheet here. So this is going to be 580B. Okay, so P2 is going to equal P1 over EXP, the exponential of QC over R air times TC. Okay. And so QC, remember, is going to be QH plus our work, and that's going to be 325 kilopascals. Divided by EXP. Sorry, I just got distracted. This right here is P1, the 325. And let's see, your QC is going to be 125, right? It's going to be, your QC is going to be 125. So it's going to be equal to 250 minus 125. Whoa. Kilojoules per kilogram divided by 0.287 kilojoules per kilogram Kelvin times 300 Kelvin. So P2 is going to come out to 76.1 kilopascal. All right, so that is our second problem. And let's move on to our final problem for the day. And this one is pretty hefty. And we're going to be dealing not with an ideal gas this time. We're going to be dealing with steam. And so this is number 581. A quantity of water within a piston cylinder assembly executes a Carnot power cycle. So during isothermal expansion, the water is heated from saturated liquid at 50 bar until it is a saturated vapor. The vapor then expands adiabatically to a pressure of 5 bar while doing 364.31 kilojoules per kilogram of work. So there's 3 parts to this. For part A, you're going to sketch the cycle on PV coordinates. For part B, you're going to evaluate the heat transfer per unit mass and work per unit mass for each process. And then finally, evaluate the thermal efficiency. So for this one, I'd like you to try it on your own first. And so give it a pause, try it out on your own, and then resume the recording when you're ready to see the solution. Okay, let's go through the solution. So the first part is sketching the cycle on a PV diagram. So let me just draw a PV diagram. And it's really hard to control the pen on my computer, so sorry, my handwriting and drawings are pretty horrific. And Thing is, we're dealing with water. So let's draw on our vapor dome. Woo. So this is our vapor dome. And some things that we are given that water is heated from a saturated liquid at 50 bar until it is a saturated vapor. Okay, so P1 is going to equal P2, which is going to be 50 bar. And the reason I know that P1 is equal to P2 is that we are going to be under the vapor dome. So actually, let me write this in a different color. So for our cycle, we are starting at a saturated liquid. So we're all the way over here at x equals 0. So we know that x sub 1 is 0. And then for P2, we are going to keep constant pressure. So this is 1, this is 2, all the way over to a saturated vapor. And so that means our quality, x sub 2, is going to be 1. Okay, because we're told saturated liquid, that's x equal to 0, and saturated vapor is x equal to 1. And we know that when we're under the vapor dome, right, for this process right here, we're isothermal. And pressure and temperature are coupled under the vapor dome. And so if we have constant temperature, we are also going to have constant pressure. So then the vapor then expands adiabatically to a pressure of 5 bar while doing 364.31 kilojoules per kilogram of work. Okay, so we're expanding here. So we're reducing pressure, but we're increasing volume. So that's going to be state 3. Remember, this is going to be adiabatic. Okay. And so the thing we know about state 4 is that we're remaining under the vapor dome. We're not back to saturated liquid or anything, but we know we're at constant temperature, so we're also going to be at constant pressure. So that's going to be 4. And we know that we're given that W, 3 is equal to 364.31 kilojoules per kilogram. Okay. And let's just do one more little sketch. So we're looking at a power cycle. So this is going to be our hot reservoir. And down here is going to be our cool reservoir at TC. And let me just draw our engine in there. Okay, so we're going to have work out in a power cycle. So W cycle is going to be done by the system. And so heat transfer is going to be from TH to the system across the boundary. Let me make sure I draw my boundary. So this is going to be QH. And QC is going to be expelled from the system to the cool reservoir. So a couple things we can look up right away are going to be our TH and our TC. So remember, since we're dealing with water, we can use the tables. We'll use the steam tables. So we can find TH and TC. So let us just open up table A3 since we are given pressure. Okay, so we're given pressure for P1 and P2 are going to be 50 bar, okay? And so this is going to be our higher temperature. So let's look that one up. So at 50 bar, the temperature associated with that is 264 degrees Celsius. So let's write that down. And TC, let's look up that one now. So we're given, let's see, we're given P3. Let's write that down, and P4. So we know that P3 is equal to P4 is equal to 5 bar. Okay, so let's look up 5 bar in our table. And we can see at 5 bar, our temperature is going to be 151.9 degrees Celsius. And this is going to be, this is table A3. We looked this up. Okay. So we know lots of stuff here. We sketched the cycle on PV coordinates. So that was A. We have some information to move on with. And so let's keep going to part B. And that is to evaluate the heat transfer per unit mass and work per unit mass for each process. So let's start with process 1 and 2, which is going to be isothermal expansion. So we have a lot of stuff to look up in the tables. So just remember that P1 equals P2 is 50 bar. TH, so T1 is equal to T2, is equal to 264 degrees Celsius. So stuff we can look up the specific volumes, and we can look up the specific internal energies. And remember, because these are control mass problems, we're not using enthalpy, right? Enthalpy is for the control volume problems where we have flow rates. Okay, so in this case, let's look up V1, and V1 is going to be equal to V sub F, okay, because that is where X is equal to 0. So let's look up that one in the table. And so here we are, specific volume, saturated liquid. Okay, and so we're going to be at 1.2859 times 10 to the minus 3 meters cubed per kilogram. This is going to be 0.0012859 meters cubed per kilogram. All right, and so U sub 1 is going to be the same thing for when X is 0, so our liquid side. And so U sub 1 is going to be 1147.8 kilojoules per kilogram. Okay, next, V2 is going to be where our X is 1, so at our saturated vapor, so VG. Okay, so let's look that one up. So at 50 bar, VG is going to be 0.03944 meters cubed per kilogram. Okay, and lastly, U2 is going to be for when x is 1. So let's look that one up at 50 bar. Okay, so that's going to be 2,597.1. And that's in kilojoules per kilogram. Okay, and so for this, we are at a constant pressure process. So when delta P is 0, do we have pressure work? Or what does it mean when we're at constant pressure, right? So for a polytropic process, N is 0 for constant pressure. So this is constant pressure expansion. So think about how to determine work from this. So with constant pressure expansion, work is going to be equal to P delta V. Okay, so 50 bar, that's the same as 5,000 kilopascals. And our delta V is going to be V2 minus V1, which is going to be 0.03944 minus 0.0012859 meters cubed per kilogram. And so W12 is equal to 190.77 kilojoules per kilogram. Box around it. And so we also need to find the heat transfer per unit mass for each process. So Q, this is going to be QH, it's going to be QH minus W12. It's going to be equal to U2 minus U1. So QH is going to equal U2 minus U1 plus W12. Okay, so that is just going to be U2 was 2,597.1 minus U1, which was 1,147.8, plus W12, which was 190.77. And so QH is going to be 1640.1 kilojoules per kilogram. Okay. Okay, we have a long way to keep going on this part, so let's keep working. So we figured out W12 and QH, so now let's look at our next process, 2 to 3, which is going to be adiabatic compression. Okay, so we don't have to find Q for this one because this is an adiabatic process. And so let's look up some more information. So at 5 bar, and we're still at x is equal to 1. So, no, we're not. What was our x? Let's just rewind for 1 second. And look at our, there we are. No, we do not know our x there. Okay, so that's something that we're going to have to figure out. So at 5 bar, if you look it up in the table, u for x equals 0 is 639.68 kilojoules per kilogram. And u for x is equal to 1 is going to be 2561.2 kilojoules per kilogram. And v for x is 0 is going to be 0.00100926 meters cubed per kilogram. And v at x is equal to 1 is going to be 0.3749 meters cubed per kilogram. All right, so let us start with an energy balance. So Q23 minus W23 is going to equal U3 minus U2. Well, we know that Q23 is 0 since this is adiabatic. And we're given W23, so that much we know. We don't know U3, but we are given U2. Or we have found U2. We looked it up for process 1, 2. And so let's keep going. So here we know that U2, or U3 for that matter, U3 is going to equal U2 minus W23, which is going to equal 2,597.1 minus 364.31, and we're going to be in kilojoules per kilogram. And so U3 is going to be 2,232.8 kilojoules per kilogram. Great. So now that we know U3, we can go ahead and we can solve for our quality, and then we can find out a little more information here. So our quality is going to be equal to, so X3 is going to be U3 minus U3F divided by U3G minus U3F. Okay, and so that's going to be equal to U3, which is going to be 2232.8 minus U3F, which is going to be 639.68. And this is kilojoules per kilogram. And then let's divide that by U3G, which is going to be 2,561.2 minus 639.68 kilojoules per kilogram. Okay. And so, in this case, we know that X is going to be 0.829, and V then is going to be 1 minus X sub 3 times V sub F3 plus X sub 3 times VG3. And so we end up with ultimately 0.311 meters cubed per kilogram. So really, this process, 2 to 3, there was nothing we needed to find because we know that Q230, we were given W23. However, we needed to know the quality for X, so we needed to know X3 so that we could go ahead and figure out our information for process 3-4. So we could solve for W34 and Q34, which is our QC. So let's go ahead and do that next. I'm going to add a new page. Okay. So for this next one, this is going to be 3-4. And this is isothermal compression. Okay, so the thing is, we know that because this is our Carnot cycle, this cycle is reversible. So we can use that the ratio QC over QH is equal to TC over TH. Okay, and so from this, we can solve for QC because we know QH from process 1-2, and we looked up TC and TH at the start of this problem, which was a while ago at this point. And so let us go ahead and solve for QC, which is going to be Q34, which is going to be QH times TC over TH. So this is going to be equal to 1640.1 kilojoules per kilogram. And now this piece you have to be very careful with, because we had looked up earlier that TC is equal to 151.9 degrees Celsius, and that TH was equal to 264 degrees Celsius. But here's the thing. This ratio only works on the absolute temperature scale, and so we have to convert to Kelvin. So TC is going to be equal to 425 Kelvin, and TH is going to be 537 Kelvin. Okay, so our ratio is going to be 425 K over 537 K. Okay, so QC, which is Q34, is going to be equal to minus 1298 kilojoules per kilogram. Because this is a heat pump, or sorry, this is a power cycle, is going from the system to the cool reservoir. So you have to keep that in mind. Sign is very important. Okay, so now let's move on to work. So doing an energy balance, QC minus W34 is equal to U4 minus U3. And once again, N is 0 for this process because of the constant pressure compression. And so W34 is going to be equal to P times V4 minus V3. Okay. So here we end up with QC. And let's sub in P times V4 minus V3 for W34. P V4 minus V3. is equal to U4 minus U3. Okay, and so here we have that QC is equal to U4 minus U3 plus, and we know that P4 and P3 are equivalent, but I'm just going to write them in, P4 V4 minus P3 V3. All right, so one thing I want us to notice, let me just rewrite this in a different order. So if we have U4 plus P4 V4 minus U3 plus P3 V3. Okay, so looking at this, we have U plus PV. What is defined as U plus PV that we can look up in a table? Enthalpy, H. So this is just simply H4, and this one is H3. Okay, so let me open up a new page so we can figure this part out. Okay, so once again, QC is equal to H4 minus H3. So H3 we can look up because we know X3. So let's rearrange and solve for H4 because we know QC. We just don't know H4. So H4 is going to be equal to QC plus H3. So H3 is going to be equal to, so we're using our tables here, so it's going to be H3 sub F, which is, if we look up in the table, 640.23 kilojoules per kilogram, times 1 minus X sub 3, which is 1 minus 0.829, plus H sub G there, so that's going to be 2007.48.7 kilojoules per kilogram times 0.829. So H sub 3 is equal to 2,388.2 kilojoules per kilogram. Okay, so H sub 4 is going to be equal to 2,388.2 plus QC, which was minus 1298 kilojoules per kilogram. So this is going to be 1090.2 kilojoules per kilogram. And I don't need to put a box around that because it's not a final answer. Okay, and now because we know H4, we can go ahead and solve for our quality. So X4 is going to be H4 minus H4F divided by H4G minus H4F, which is going to be 1090.2 minus 640.23, and that's just looking up in the table since we know our pressure and our temperature actually. And then we're going to divide by 2748.7 minus 640.23. I didn't write the units down just because it's a ratio and they're going to cancel anyway. And I'm trying to save some room. And so this is going to be x4 is going to be 0.213. Okay, and so because now we have x4, we can go ahead and figure out v4. So v4 is going to be 1 minus x times v sub 4f plus x times v sub 4g. Okay, and then ultimately you're going to look those values up in the table, use the x from above, and you end up with v sub 4 is equal to 0.0807 meters cubed per kilogram. And then lastly, we can get our work. Whew. So W34 is going to equal P delta V. Since N is 0, this is constant pressure process, which is going to be equal to 500, because we were at 5 bar, kilopascals, times 0.0807 minus 0.311 meters cubed per kilogram. And so this is going to be W34 is equal to minus 115.15 kilojoules per kilogram. Okay, almost there. We have one more process for part B. Let's add a page for the last time, hopefully. Okay, so this is going to be process 4.1. And this is adiabatic compression, so at least we already know what Q is, and Q is 0. Okay, so here we have Q41 minus W41 is equal to U1 minus U4, and we know that Q41 is 0. And so then we can just rearrange, and we know that W41 is going to be equal to U4 minus U3, since I just distributed the minus sign. I mean U4 minus U1, since I just distributed the minus sign. And we know U4, or we can figure out U4 using the tables and know our knowledge that X is 0.213. So U4 is going to be 1 minus 0.213 times our U sub V, which is going to be 639.68. And this was at 5 bar kilojoules per kilogram, plus 0.213 times 2,561.2 kilojoules per kilogram. And this is going to be 1049 kilojoules per kilogram. So, and we had, let's see, I think we had already had U1 earlier, so let's just use our number from that. So W41 is going to be equal to 1049 minus 1147.8 kilojoules per kilogram. And so W41 is going to be equal to minus 98.8 kilojoules per kilogram. Ha, we did it. That is part B of this problem. Part C is much, much quicker. And so let's just look back at a couple things before going onward. So I want you to notice X4 is around 0.2 and that X3 is around 0.3. Sorry, X3 is around 0.8. That makes way more sense, which is why I paused for a minute. All right, so looking back at our PV diagram, right? So X3 is about 0.8, so we're about 80% of the way across the vapor dome, and X4 is around 0.2, so we're about 20% of the way across the vapor dome. So it makes sense. It's always good to look at your work and just think about whether it makes sense physically. All right, lastly, let's go down to, can I get there? No? Let's move my face for a sec. There we go, C. Okay, so now a quantity of water within a piston cylinder assembly, I don't need to read that again, but part C is to evaluate the thermal efficiency. So this isn't so bad. We've already done most of the work at this point. So the thermal efficiency is our eta. And remember, the thermal efficiency is equal to W cycle over QH, which we know, well, we know all our W's, so now we can find W cycles. So W cycle is going to equal W12 plus W23 plus W34 plus W41. And so this is going to be equal to 190.77 plus 364.31 minus 115.15 minus 98.8, and this is kilojoules per kilogram. So W cycle is going to be 341.13 kilojoules per kilogram. And so our efficiency, eta, is going to be equal to 341.13 kilojoules per kilogram divided by QH, which was 1640.1 kilojoules per kilogram. So this gives us an efficiency of 0.208. So after all that, it's about 20% efficient. Okay, well, there you have it. Thank you so much for sticking with me on this. And if you have any questions, run into any snags, feel free to post to the forum at the end of the weekly content, and I'll be checking that regularly, and so I can respond to the whole class. If not, you can also email me, and we can figure out a way to chat there. All right, well, I will see you next time.